Section 11.5 is on page 689. Talks about areas and length in polar coordinates. We're going to focus on area. I'll touch on length really quick, but we're going to focus on area a lot more. I need to remind you that the area of a sector, if you're given a circle with a radius of r and the angle theta, this s is called the arc length. S is r times theta, if you remember, and the condition on this was that theta must be in radians for this to work. And on top of that, the area of the sector, the area of this shaded part, was 1/2 r squared theta. That we learned back in the days in trig. Now, suppose I have r equal f of theta, and I want to find the following area. Let's say I want to find this specific area. Well, we have a small problem. R equal f of theta is not a straight line, it's a curve. So, if I take this, this area, and I cut it into sectors, and if I take one of those sectors, let's say I take this sector right there, and I blow that up, this is really what I'm seeing. That would be the area of that sector right there. Oh, you know what? I messed up. I forgot. When you color those two, you get green. I just want to match it, so we're seeing. Oh, come on. Dude. Here we go. The area of that piece. Now, if I know that this angle right here is theta, and the angle right here is beta, when I look at this, I'll say, well, let's see, this is r right there, and this right here is actually s, right? And if I want to find this area, this is the area of, if I call this r sub I, s sub I, right? S sub I is actually r sub I times theta, right? Whatever the change of this is, let's call it I. And area is 1/2 r sub I squared theta sub I. Well, and I know that r is, I know that r is f of theta, so I could say area would be 1/2 f of theta sub I squared times the change of theta sub I. Or I could say, if I want the total area without making this really long, I'm going to integrate from theta to beta, 1/2 r squared d theta. And that will pretty much find me that exact area, right? Some would write it theta to beta of 1/2 of f of theta squared d theta. It doesn't really matter, it's the same thing. Now, another thing I want to get out of the way, and that is, if I was looking at r sub 2 equal g of some theta, and if I was to eliminate there we go. If the area in question is really this area, then this is really how I'm going to tie this down. I'm going to say area is going to be the integral. It's still from theta, and it's still running to beta. That didn't change. It's still 1/2, but if I run an arrow, and that's pretty much how I see this. If I run an arrow of f of theta squared d theta, that will get me all of this. If I take the integral from theta to beta of 1/2 g of theta squared d theta, that will get me this area, because the arrows run to right there. And if I subtract the two, guess what? I'll get the desired area. So basically, anytime I want to find the length of the area of a polar sector, I run my arrows and simply take tip minus base, just like we did in rectangular. We took the top minus the bottom. Remember that? F of x and g of x. The same idea here, except when you draw those arrows, you want to take the tip of the arrow minus the base of the arrow. And you could combine those into one. And the same warning as we did in calculus back in the days, from theta to beta, 1/2 is a constant. Make sure that you take f of theta and you square it minus g of theta and you square it, not the quantity f of theta minus g of theta, the whole thing squared. That doesn't work. Just like you did back in the days when we did the washer method, if you recall. So that's pretty much it for this. The hard part is the graph, really. Not much the integration and the work. You end up using 8.4, most of the time. The integral of sine squared or cosine squared, that is, use power reduction and you proceed. The graph is half of the problem. This is on page 693. So, if I was to go ahead and figure out what the area is, this is how it works. I'm going to set up those integrals. I'm going to integrate, and let's see how this works. Here they told us you start at pi over 4. So you start at pi over 4. And we could see that you're terminating at pi over 2. So visually is a big deal, of 1/2. And I notice if I run my arrows, the tip is this function and the base is 0. So it's simply twice the sine of theta squared d theta. And again, this is going to be sine squared. Remember that sine squared of theta is 1 minus the cosine of 2 theta divided by 2. And cosine squared of theta is 1 plus the cosine of 2 theta divided by 2. And sine of theta, let's go this way. Twice the sine of theta cosine of theta is the sine of 2 theta. So sine of theta cosine of theta is the sine of 2 theta divided by 2. If you remember that, you're in a very good shape. The last you could really use trick substitution. Let u equal sine du will be cosine, not a big deal. But that's pretty much what you need for those. And you could do the rest. It's not that challenging. And they seem to give us the graphs for the first two problems. Not that we need the graph. We already know how to do all of this. For example, if I was to say graph r equal the sine of 2 theta, you know that's a circle wrapped around the positive y-axis, right? How do you know that? Well, sine is the y, and that's positive with a diameter of 2. So we can get that graph easily. Here, they're not doing us a favor by giving us this graph because we know that area is going to equal the integral. So we know if we run the arrows, that's the tip, that's the base. So you're running to cosine of 3 theta squared d theta. You could use symmetry and say 0 and multiply that by 2 if you wish, but you need to know where this terminates. So we need to know the beginning and the terminating side of this. This graph doesn't help you with that. Actually, what we did in the previous section, 11.4, we mastered this. We really don't need them to give us a graph. And they only provide the graph on the first two problems. The cosine is a graph that looks like this. This is 2... Oh, come on. 2 pi over 3, half of that pi over 3, and half of that pi over 6. So if you remember from that, we know you start at 1, decreases by the time we hit pi over 6. Oh boy, that's an awful 6. By the time we hit pi over 6, we are at 0. Well, guess what? You decrease, this is pi over 6. That's all I need. Or I could say area equal the integral from negative pi over 6, because I know this is negative pi over 6, to pi over 6 of 1/2 cosine of 3 theta squared d theta. And there it is. On number 8, I'm going to alter the problem. I'm going to make that a 4 of theta, because 3 odds don't get affected by the squared, but they don't come up. There's only one problem that's odd. Majority of the problems we come across are evens. So let's assume it is even, and this is what we know. We know we're going to ignore the square. If you remember how we did this in the previous section, r equal 2, r equal negative 2, and we label those clearly if you remember. Sine starts at the origin, runs up, back down to the starting point. That is one full cycle. That's how we graph those. This is 2 pi over 4. This is half of it. This is half of that. So pi over 8, I need to break this into 4 equal parts. Let me show. So what I did, since this is pi, and I need pi over 8, that's 8 pi over 8. So I need to break this into 8 equal parts, or each quadrant into 4 equal parts. 1, 2, 3, 4. This is 1 pi over 8. This is 2 pi over 8. 3, 4, 5, 6, 7, 8. 9, 10. I don't need all of those, of course. Now, I'm going to use symmetry. It says, find the area inside this 6-leaved graph. It's really 8-leaved graph. Well, let's see how that works. If I look at this, and I start at 0, I am at 0. This increases. By the time I hit pi over 8, I am at 2. There's pi over 8, and there's 1, 2. And pretty much I'm done with the problem. Because if it took pi over 8 to get the bottom half, it's going to take pi over 8 to get the top half. This is, as is, an 8-leaved graph. So there are 2 pi over 8 apart. So 1, 2, the next time, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, and 1, 2. And you could sketch a graph. There's no need to do all of that. It's not needed. But I do want to point out the practice that we've been doing, just to make sure that we're getting this. And these are the 8 parts. Now, I know area for one of those is going to be the integral. I could run from 0. Do you see? I could run 1/2 of r squared. It's already squared. And I could say, on this, I could say that if I multiply it by 2, I'll get the upper half. So that's one area, one pedal from 0 to pi over 8. Or I could ignore that and run to pi over 4. That'll work. So basically, I could get the bottom half of this pedal and multiply it by 2. Now, how many pieces are there? When you square root both sides, do you remember how we did that? We said this can no longer be negative. Isn't that negative between pi over 4 and 2 pi over 4? Since it's negative, you can't have that pedal, and those are symmetric, so you end up eliminating half, and it's really 4-leaved graph. So if I have 4 of these leaves, and this is the area of one of them, multiply this by 4, and that gives you the area of the whole thing. And that's how this works.